Let's go ahead and write down, or at least note what I've written down about what we know about what's going on here. It seems like what's going on here, we got a electron of charge negative 1.602 times 10 to the negative 19 coulombs and a mass of 9.1 times 10 to the negative 31st kilograms. And it exists in a contraption of 5,000 volts. So it looks like a parallel plate capacitor, which has 5,000 volts in between it, between A's and B, points A and point B. So first of all, let's look at the things that we do know. We know that the electron starts off at rest. We know that it'll just start its position at 0. We'll know that the negative side of the parallel plate capacitor is 0 volts. And we will note that the positive side where the electron finishes is at 5,000 volts. Okay, so first let me make a little note about how to start this. So there are two ways of using physics equations. The first way is by forcing all parameters to be positive and by artificially putting a negative in the equations so that you can have full control over if things are positive or negative based on your coordinate system. For this particular problem, however, I'm going to go ahead and put the negative within the parameter itself. So I'm going to write down the original equation, and then all negatives are just going to be summoned within the parameter that we're dealing with. So let's go ahead and do part A first. The equation for that is W is equal to delta U. And U is Q times voltage. So if we're taking a delta of Q times voltage, we're going to look at Q times voltage final minus Q times voltage initial. Right off the bat, we can see that the initial voltage is 0 from our knowns, and that leaves us with the final voltage of 5,000 volts. So the work done to this electron during its journey from one plate of the parallel plate capacitor to the other is just going to be Q times 5,000, and that ends up being negative 8.01 times 10 to the negative 16 joules. And as you can see, there's a negative value, so it does negative work. Let's do part B. Part B invokes the conservation of energy equation because they want to know the velocity. So let's go ahead and look at the difference between small v and big V. I put little hats on top of the big V. So the conservation of energy says that the potential energy initial plus kinetic energy initial of the electron is equal to the final potential energy plus the final kinetic energy of the electron. We know that the electron starts off at rest. Since V naught is 0, we'll say that this whole term is 0. And it starts off at the 0 volt plate of the capacitor. So this is also 0. So we end up seeing that 0 is equal to Q V final plus 1/2 m little v final squared. Okay, now all we got to do is just isolate V final and plug and chug. V final ends up being negative Q big V. We'll bring over the 2 on this side. We'll divide by m. And then we'll take the square root of both sides, thus leaving V final by itself and everything else here to the right by itself. So since Q is negative, then this negative will go away and it'll just be 2 times 1.602 times 10 to the negative 19 coulombs. Everything else is positive, so this is not an imaginary number, it's a real number. It ends up being 4.1957592 meters per second, very long number. So it's going to go really fast at the end of the capacitor. And to get it into SI units, let's go ahead and see how many SI units are around here. Looks like only 2 because the mass of the electron that I wrote down at least yields only 2. What's given though is 4 significant figures with the voltage. So if I were to really want to look up at least 4 significant figures for an electron's charge and mass, I could do that. And that would end up saying that this right here is 4.196 times 10 to the 7th power meters per second. And you can go ahead and say that's your final answer for the velocity of the electron. Here are my 2 answers: the work being done on the electron and the velocity of the electron after it moved from one plate to the other plate of the parallel plate capacitor.